From the beginning of human civilization, we have all subscribed to different ideas of not only how our world will end, but the entire universe. Whether it's linear time where we live now and it ends in the future, or perhaps the cyclical worldview with decay and rebirth, analogous to the cyclical universe that I described in my Big Crunch video from before, or even a universe which doesn't really end and just goes on forever. Given all these conflicting ideas of the end of time, how on earth does one approach the study of the end of the universe in a scientific way? Well, for that, one must look at what are known as the Friedman equations. These equations can give us amazing insight into what three potential end of the universe scenarios may look like. These equations essentially govern the expansion of space in homogeneous and isotropic models of the universe within the context of general relativity, where homogeneous and isotropic refer to the fact that the universe looks the same in all directions. I covered the evolution and ending of a closed spherical universe in a previous video, so if you want to see that, check the link in the description below. So, we live in a flat universe, as far as we can tell. This means that the geometry of the universe is such that if you drew a triangle on the surface of the universe, all its angles would add up to 180 degrees. This isn't the case for a universe with a spherical or hyperbolic geometry. What does this tell us about our universe's evolution though? If you recall the Friedman equations from my previous video, we have a curvature parameter, but here instead of the curvature parameter being positive as it is in a spherical universe, we have the equations with the curvature parameter equal to 0. So in a flat universe with no dark energy, I'll come back to that point later, our universe expands forever but at a continuously decelerating rate. So the expansion asymptotically approaches 0. However, contrary to Einstein's ideal universe, which was static, we do have dark energy, and this causes our universe to expand at an accelerating rate. Dark energy is simply this mysterious force that is causing our universe to continuously expand faster and faster and faster as time goes on. We have really no idea what it is or what's causing it or where it's coming from. It's probably one of the biggest mysteries of all time. So in our universe with dark energy, the expansion rate of the universe initially slows down due to the effect of gravity, just like in a closed universe, but it eventually increases. And as I already said, the expansion rate not only increases, but it increases at an accelerating rate. So it's getting faster and faster as time goes on. So with our closed universe from before, we could tell that our universe was expanding and then it would come back on itself in a big crunch. The ending of a flat universe is a bit more chill than that, however. A universe that will expand continuously with nothing to slow it down will end in a heat death. So that's the fate of our universe. This is when the universe reaches thermodynamic equilibrium. So basically, no more work is done in our universe. No energy transfer is happening. So everything is just paused essentially. I think the best example is, imagine a closed system where you just have a mug with tea and you pour milk into it. The tea and the milk eventually mix together and become the same temperature. Assuming there's no energy transfer to the outside environment, there's essentially no more action happening. That's analogous to how our universe will end. So there's no actual specific temperature that the universe will be, so I guess the term heat death is slightly misleading. I'm sure you're probably wondering, what is the timescale of this supposed heat death? Well, the decay time for a supermassive black hole of roughly 1 galaxy mass, which is about 100 billion stars, because of Hawking radiation, is on the order of 10 to the 100 years. So entropy can be produced until at least that time. That is 10 followed by 100 zeros. Hawking radiation is basically a proposed mechanism that allows black holes to evaporate. The timescales that this would happen though are so long that it would be impossible to detect this actually happening. Some large black holes in the universe are predicted to continue to grow up to perhaps 10 to the 14 solar masses during the collapse of superclusters of galaxies. But even these would evaporate on the timescales of 10 to the 106 years, which is 10 followed by 106 zeros. At that time, the universe is expected to consist mainly of just photons and leptons. No stars, no planets, no galaxies, no anything. After this, it gets too sci-fi to even enjoyably speculate about. I don't even think 10 to the 106 years is a concrete estimate in and of itself, but it's so far in the future that I am not concerned. So that's the end of our universe, a geometrically flat universe with dark energy, and that is also the end of this video. So I will see you soon for another video about astrophysics. All links and other references to this video are in the description below.